Let us now look at the process by which we build regression trees. Of course, when I say we build regression trees, I'm actually talking about how a computer-based algorithm would be building regression trees. But again, it's useful to understand that process so that you can interpret the results correctly. Okay, so we are back to our data set with income, family size, and expenditures. Okay, so let's first calculate the overall deviance or overall heterogeneity for this data set. So the mean expenditure is 591.75. If you calculate the mean, that's what you'll get. And the deviance is the measure of heterogeneity, is essentially the sum of the squared deviations for every single value, which means we take the first value 765, subtract the mean from it, so take the difference from the mean, square it, take the next value, take the next value, and so on and so on and so on. Okay, so if you do that, if you go through that entire process, I've got all the cases covered here, you find that the total deviance is 478,513.8. Okay, so that's the total deviance. And of course, we are building regression trees. And it'll be, again, good, like we did with classification trees, to visualize what's going on. So I've created this chart. Okay, so in this chart, what you're seeing is, again, because we've got only two predictor attributes, we can visualize this on a two-dimensional surface, and it's useful to understand the ideas. So we've got income on the x-axis, we've got family size on the y-axis, and the individual points are all here. And what I've done, instead of just placing a point, I've put the actual expenditure at the position where the point would be, right? So this, for example, represents a family whose income is less than 60,000, so it's 50 odd thousand, and the family size is 2, and the expenditure is 350,000. So let's see if we can locate that here. 350. So let's see that here, 350. Okay, this is that particular family. Income of 56,000, family size of 2, expenditure of 350. Okay, so that's what we are seeing here. So similarly, that's really what this represents. And we've already calculated, this plot contains some overlapping points. In other words, for example, at 765, there's not one row. There are actually a couple of rows that fall here. And of course, because of the nature of the plot, they completely overlap. So for example, if we went back to our data, we would see a couple of 765s. Okay, so there's one 765 right here, and there's one right there. Okay, and both of them have exactly the same income, 136,000, 136,000. Okay, so that's what's going on. That's what I mean by saying that the plot contains overlapping points. Okay, now the total deviance for this data, we have already calculated as 478,514. That's the amount of heterogeneity that exists, right? Because this is a large number, which means what? Which means the values are all quite different from each other. So when you calculate the difference of each value from the mean and add up the squared differences, it comes out as a pretty large number. Okay, so that's what it is. Now what we are trying to do, of course, is to look at all the possible. This is the root node. The root node contains all the cases in our data set, the 20 cases which are in our data set, right? Now we want to split the root node into two nodes, that is, place a split somewhere so that the 20 cases are split into two sets. And we want each of those two sets to be more homogeneous than this, than the overall data, right? That's what means that the split we are performing provides some kind of an improvement. Okay, so we are going to look for a split that reduces the deviance the most, right? Which means what? Which means we have to consider all the possible splits, right? So we can split this data along income in many different ways. We can also split it along family size in many different ways. Okay, so let's say there are X number of splits possible on income and Y number of splits possible along family size. The total number of splits we have available at this point is X plus Y. What we want to do is, from among these X plus Y splits, we want to choose the one that reduces the deviance by the maximum amount. That's really what we are trying to do. So at every point we are trying to see, well, what is the best split I can do at this point? Okay, so in order to determine all the possible splits, what I'm going to do is first consider income and consider the income in sorted way, right? It's consider all the incomes sorted, right? So clearly, if we have these incomes, then between 50 and 56,000, we can split the income at any place. It doesn't matter. The way in which it's going to split the data is going to be the same, right? So you can split either at 51,000 or 52,000 or 51,992. It doesn't matter, right? So all we want to do is to consider the first possible split on income occurs between 50,000 and 56,000. And for convenience, I'm just considering that the split will occur at the midpoint of the difference between. So 53,000. Similarly, you can have a split between 56,000, 56,100, which is at 56,050, and so on and on and on and on. So these are all the possible. Notice that there are two 78,000s, and therefore, obviously, there is no need to split between 78,000. So the next split here is 78,050, which is halfway between 78,000 and 78,100. Okay, so that represents all the possible splits that we need to consider on income alone, right? Which means that we have 16 possible splits on the income dimension. Similarly, if you consider the family size, there are not that many splits possible on family size because the only values for family size are 2, 3, 4, and 5, right? So we could have a split between 2 and 3 at 2.5, could have a split between 3 and 4 at 3.5, and between 4 and 5 at 4.5. So there are only 3 possible splits to consider on family size. So overall, you've got 16 possible splits on income and 3 possible splits on family size for a total of 19 possible splits. Okay, so what we want to do is to consider each of those 19 possible splits, and for every one of those splits, calculate the resulting deviance. Okay, and choose the split that gives us the lowest possible deviance among all of them, which means that's the split that gives you the maximum possible heterogeneity at this point, homogeneity at this point, because we want each of those sets to be as homogeneous as possible. And at this point, if you consider all the splits, the best you can do is to choose the one that gives you the maximum homogeneity, which is the minimum deviance. Okay, so that's what we are trying to do, and we'll see a concrete example shortly. Okay, so let's take a deviance computation example for one example. Okay, of course, again, I emphasize these are not calculations we actually ever have to do. We don't have to do these calculations. You know, when you call the function to build the regression tree, R is going to do all of these things, right? But I just want to show you the logic of splitting. Okay, so of course, in order to do that, I'm going to take one split and calculate its deviation, its deviance. Okay, so let's say that we consider a split on income at 76,500. This is just some, one possible split. Nothing, it's not that it's the best split or the worst split, nothing. Just want to give you an example of the calculations. Okay, so suppose we want to split at 76,500 for income, right? I'm just going to use some of the dplyr functions that we learned. So I'm saying library tidyverse, and I'm reading the data vacationexpense.csv, right? And if you want to split at income of 76,500, so of course you'll get two sets. One set for values which are less than 76,500 or less than equal to 76,500, and another set for incomes which are greater than 76,500. Those are the two sets I'm creating here. V1 is V filter income less than equal to 76,500, right? So V1 will contain all the rows of V which have income less than 76,500, and V2 will have all the rows for which income is greater than 76,500, right? Now, to calculate the resultant deviance or resultant homogeneity or heterogeneity, all I have to do is to calculate the homogeneity or heterogeneity for V1 and V2 and add them up, right? So consider V1 first. So I'm saying V1 dollar expenditure minus mean of V1 dollar expenditure. right? That's after all what you do. You take the deviation of each value from the mean, square the deviation, and sum them all up. Okay, so this first line here is the deviance for V1, and the second line here is the deviance for V2, and we are adding the two up. Okay, so the resultant deviance is 291,580. Okay, remember, for the overall set, the deviance was 400 and something, 478,514. As a result of the split of income at 76,500, we can reduce the deviance to 291,580. Okay, so the deviance has reduced, so we have improved the homogeneity. Of course, I'm not saying that we have found the best possible homogeneity, because that would require that we consider all the 19 splits. This is just one split, right? So what we would want to do is to repeat this calculation for all the 19 splits, and for each one compute the deviance and choose that split which gives us the lowest possible value for deviance. Okay, so let's take one more example for deviance. This time I am considering a split of family size at 2.5. Right, so again, I'm doing V3 and V4, and we are filtering family size less than 2.5, family size greater than 2.5, added up, and we get a deviance of 405,006. Okay, so clearly this split of family size at 2.5 is nowhere near as good as this split, because here notice the deviance is 291, which is far less than the deviance here, 405. Okay, so this is probably not a great split. That is a much better split.